Now we're going to talk about bond length, which has a lot to do with bond strength. Just in the bond energies we saw got a lot larger as we went from single to double to triple bonds, and that's more shared electrons and it decreases its size. So in a covalent bond, the distance between the nuclei of the bonded atoms is called its bond length. So it's that distance between the nuclei is the key part. And so the actual bond length really depends then on the atoms that are participating in the bond and the atoms around the bond. And so we usually look at an average bond length for similar bonds in many compounds, rather than looking at it for one specific type. So we see some trends emerge when we do this. We see that the more electrons two atoms share, the shorter the covalent bond. So that's really going to mean our triple bonds are shorter than our single bonds. Let's do it like this. We also see that the bond length will decrease from the left to the right across the period. Remember, these atoms are also getting smaller as we go across the period. We're seeing our net Z effective, our effective nuclear charge, increase as we go across the periodic table. And so that's going to create a greater attraction to the electrons that are shared. We see that our bond length will increase as we go down the column. And remember, we saw that size increased down the column as well. And so the size of the atom is getting larger, which is just going to force those nuclei to be further apart because the interacting piece is the valence electrons, and there's more distance between the valence electron and the nucleus of either atom. We also then see as the bonds get longer, they get weaker. So they're easier to break. It requires less energy to break them. Here's a table with some example bond lengths. And I'm going to focus, since we focused on nitrogen for the bond energies, I'm going to do the same here. So our bond length is in picometers. Remember, 1 meter equals 10 to the 12 picometers. So we're talking about something really small. Our single bonded nitrogen atoms are 145 picometers, where a double bond gets shorter, it's 123. And a triple bond is 110. So as we increase the number of bonds, we decrease the actual size between, or sorry, the length of the bond. We can also look down the periodic table as well. So let's take something like an oxygen-oxygen bond versus, I don't have a sulfur-sulfur. Let's go down the halogens. So my fluorine-fluorine is at 143. And then as I go down the periodic table, I see that same halogens, but now it's chlorine on the next row, but a single bond still gets longer. So and then same with bromine and iodine. So as I'm going down the table, a single bond between two halogens gets longer and longer as the size of the atom increases. Looking across the periodic table as well, I don't know if we have any good examples of this. We can go carbon, carbon, oxygen, oxygen, and nitrogen, nitrogen, I think. So our carbon-carbon bond is 154. And then if we look at the nitrogen single bond, now this is going across the periodic table. So nitrogen is to the right and it gets smaller. And then if we go to an oxygen-oxygen single bond, so going another element to the right, it gets smaller-ish. It's the same. Maybe not the best example, but we should see a slight decrease as we go across.